možemo staviti u džep. Ja ću danas govoriti hrvatski jer nemamo slušača. Može da pitamo kolegicu da li je još, samo je ona u Osijeku, niko drugi nema, jel? Da. Ali onda će napravit ćemo engleski zato jer da oni mogu poslije toga koji nisu tu vidjeti snimku. Ok. So I apologize for the delay. And I'm going now to recapitulate some of the matter which I have done last time. And this was the introduction into constraint minimization.
Me čujete?
And so I have to okay. And we had an example which I will now repeat. Minimize Vxy is equal to x times y, and the condition was x minus 2 square plus y minus 2 square minus 1 being equal to 0. And the first observation was this is a circle, so it is compact, and the minimum and the maximum is taken. The function is continuous, so it's trivial. Now, I draw also a picture this is the constraint, and those are the lines of niveau of constant values of the function to be minimized. So this is V is const. And the observation was if the function is growing in this direction, then the maximum will be taken here and the minimum here, just where the constraint touches the niveau line of the function. That's the heuristics. Well, that means the orthogonal, the normals to this curve has to be parallel to this one. So that means that dv over dx plus lambda, that's parallel, dg over dx equals to 0, and dv dy plus lambda dg over dy equals to 0. The normal to the circle is given by this vector, and the normal to the constraint is given by this vector. Let's just ask for them to be parallel. So, applying this we get the following. Y plus 2 lambda x minus 2 equals to 0, and x plus 2 lambda y minus 2 equals to 0. Plus this, of course. It's 3 equations for 3 values, x, y, and lambda. Now, those equations, if we write them properly, 2 lambda x plus y equals to 4 lambda, and x plus 2 lambda y equals to 4 lambda again. The determinant of this is equal to 4 lambda square minus 1. But the cases where this is 0 are impossible. I'll not discuss it once more, I will just repeat. You cannot solve all 3 equations with this supposition. So we have y equals to x equals to 4 lambda over 2 lambda plus 1. So now, because the whole problem has a symmetry with respect to this line. So now, taking this together, you get 2x minus 2 square equals to 1, and this gives x plus minus equals to 2 plus minus square root of 2. Both of them are positive. And the v of x plus y plus is obviously larger than v of x minus, because function is monotonical. So out of this data, we conclude x plus y plus give maximum, and x minus y minus gives minimum. And this is sometimes enough, even if you think rigorously. Once you accept that this is the necessary condition for having a minimum or maximum, then you solve the equations. The only possibility are x plus minus and y plus minus. There is minimum, there is maximum, and you just check the values up and down. So much for this concrete example. Now, of course, here another possibility is given. You can eliminate independent variables, for example, by taking polar coordinates. So this is then a V. I still use a non-orthodox way of writing Vxy equals now to V of phi. I use the same symbol, which is now equal to what? R square sine 2 phi over 2. Well, now you can differentiate this because it is now one variable. This is R square cos 2 phi, and this is equal to 0 for phi equals to p half or 3 pi half. That's this. Oh. No. Here is wrong. That's correct now. So you see, just one angle is here and the other is here. Well, that's an easy way, and you should try it if possible, but it is almost so rare that you can forget it in practical computations. It's easy, and it is nice to have it in your head, but especially if you have to work with many parameters. So, now the general recipe is to write down the so-called function of Lagrange. This is V plus lambda 1 G1 lambda S GS, where G1 to GS equals to 0 describe the constraints. That's the general way of solving this constraint problem. You first form the Lagrangian function. Well, and then take the gradient of it, dl equals to 0, and solve these two. That's the rule, how to do it. Well, again, you see that means that that means dl equals to dv plus well, here I can also write down if g is equal to g1 to gs and lambda is equal to lambda 1 to lambda s, then you can write down this plus g transpose times lambda. That's a compact way of writing it. So what that means? Well, that means that the gradient to the function is parallel to the gradient of a linear combination of gradients of GT. So, some theory. Theorem, let M be defined by G equals to 0. Twice continuously differentiable on a convex region omega out of Rm. You remember, region means open and connected. And let x0 be a stationary point. Sometimes such points on which you look, your functions here are called configurations, just suggestively looking at the geometry of it. Stationary point, that means dv of x0 plus dg x0 times L is 0. And the second derivative is positive definite over omega. So these are the assumptions. You see, once you have solved this, you have a solution. We now suppose we have a solution. So you have also lambda, which is now given. And now you fix lambda, and you let x vary for this fixed lambda. And you get a function just of on omega. And if this function has the positive definite derivative all over all of omega, then x0 is unique minimizer of V on M. That's the theory. As you will see, the proof is extremely simple. First of all, consider the function h of x being equal to v of x plus, now I changed the name, it's just the Lagrangian.
Pustite, ja ne vidim ovaj dio ploče.
Ge of x. This function has the property that its derivative is equal to 0 and its second derivative is positive definite. We know, we have proved it before, that such functions can have only one minimum in this convex region, and if the gradient is somewhere 0, then this is the unique minimum. That's the thing we know already. We have proved it before. Now, but we know that this is 0. Where? For x, so we have dh x0 0. That we know, that we have supposed. But now, x0 belongs to M, and M is a subset of omega. So h takes its minimum, the same minimum, if restricted to M, of course, because it is a subset. But then, on M, the function h is identical with the function v, because there we have g is equal to 0. So we have h of x is equal to v of x of omega. S of n. Now that's the proof. Well, what can be said about this proof? It's extremely simple, it's almost trivial. Thank you. It's almost trivial, so there must be some catch. Where is the catch? You have to ask positive definiteness of this function over all of omega. And in fact, that's too much. This positive definiteness should be somehow fulfilled only on this manifold, because that's where you look for a minimum. Sometimes you will have it, this condition. That's easy, that's nice, but not always, mostly not. So we will have to look for something better. Now, before I go further, I would like to come back now to this example. Back to this example. You see, the second derivative is just the matrix of this system. You just differentiate once more. So dl is equal to 2 lambda 1, 1, 2 lambda. And now look for positive definiteness of this matrix. Well, lambda should be just large enough. If they are not, for example, smaller than 1, then the matrix is not positive definite. Just look at the determinant. So, determinant we know is 4 lambda square minus 1. And what do we have here? Let's look at x minus. X minus, y minus. What do we have there? We have there, well, here. X minus equals to y minus equals to 2 minus square root of 2. And from here, and this is equal to 4 lambda over 2 lambda plus 1. So we have from this, we have 2 lambda plus 1 x minus equals to 4 lambda. And that means that 2 lambda is equal, this you get here, to 2 square root of 2 minus 1. And this is larger than 1. Larger than 1. So it's positive definite, and you have a it's positive definite, and so we have a minimum there. And vice versa, if you take x plus y minus, x plus y plus, then you will see that this lambda, 2 lambda, is smaller than minus 1. So it would be just a negative definiteness. That's the maximum. Okay. So that's fine. On this example, we have our theory works. So now let's look at another example, which the v of x, y is equal to, again, x, y, but now our g is equal just to x minus y. Yes. So the Lagrangian here is equal to L is equal to V plus lambda G is equal to x, y plus lambda x minus y. And the derivatives are y plus lambda x equals to 0 and x plus minus lambda y equals to 0. It's easy. With the solution, y equals to x equals to lambda equals to 0. Well, but now the second derivative is lambda 1 minus lambda 1 1 minus lambda x lambda yes. And this is indefinite for lambda equals to 0. It's 1, 1. So we have no possibility to apply this simple theorem. But let me make one more remark here, which also shows how special this situation is. We didn't need any regularity property of the manifold defined by the conditions. No matter. No regularity needed. I should stop my lecture, but I will now continue at least a couple of minutes. No regularity. Well, let me just make a small historical remark. Lagrange was living in somewhere in the middle of the 18th century. It is 250 years ago. And the tools of mathematics at that time consisted practically only of which you now heard from me as heuristics. That's what they knew. It was heuristical, no logic foundation of no theorems, no proofs, nothing. And of course, that's why it was not easy to learn this. You must be really a very, very gifted mathematicians to grasp their reasoning, which is completely heuristic. And a great Croatian mathematician and astronomer, Ruđer Bošković, was completely aware of his mathematical ignorance and was complaining in it in a letter to his brother. And he said, you should learn this quite young, like learning a language. That's quite interesting. And a more interesting remark is that this remark from him was written not in Italian, which was his normal language, but in Croatian, such as only his brother would understand it. He was ashamed of being ignorant. Okay, so let's go back to this. To this example. What's that's the condition, that's the constraint. And what is the tangential space of this? It's equal to the manifold because it's linear. See, the tangent manifold is the constraint itself. So if you now there's this matrix on the vectors from the tangent space, what are they? They are just, they have the same components. Well, that's equal to lambda that is lambda lambda x lambda plus 1 psi 1 minus lambda psi and that's equal to what? That's lambda plus 1 xi square plus y minus xi square. And that's equal to what? To 2 xi squared, and that's positive. So this is just a heuristic now. You look at the second derivative, the form, the positive definite is a matter of forms. You see? X that's what decides about positive definiteness. So now we have to look at this form restricted to the tangent space. And there it's positive. So it will be minimum if it would work, the whole theorem. No, it works. It works, and that's a new theorem. So I don't need the old theorem anymore. There is a new one. Well, it's not quite a generalization because, you see, the old theorem, in fact, gives us a unique minimum. It's a point which the new theorem wouldn't be able to. It would give just a local result. So theorems. Let V G be twice continuously differentiable. M omega as above. And x0 from M be a local minimizer. Of V restricted to M. Then d v of x0 plus dg x0 times lambda equals to 0, of course, for some choice of lambdas. That means there is an x0 and there is a lambda such that this is solved together with, of course, moreover, psi t d2 x0, excuse me, v of x0 psi is greater or equal than 0 for psi from the tangential space for the manifold, of course, taken at x equals to 0. Conversely, if in addition a stronger inequality holds, namely psi transposed d2 v of x0 psi is greater or equal than some delta norm for some delta positive and psi from the tangential space. Then x0 is a unique local minimizer of V restricted to M. Well, it is a short way of speaking local minimizer of, I should say, at x0. That means there is a neighborhood of x0 such that x0 is an absolute minimizer on this neighborhood. Well, you see, this is quite parallel to what we know about standard minimization of a function of one or more variables. The function has to have a derivative equals to 0, and the second derivative must be positive, not negative. And if it is positive, non-negative. If it is positive, then the minimum is unique. That's just the same thing we have here. Only the technique is a bit different. So now we let us to have a small break. I would say in 10:20.